this video, I'm going to discuss a left-tailed hypothesis test for population proportion. So let's go ahead and read the example first. A foreman claims that less than 5% of the products on her production line have a defect. A random sample of 845 products found that 40 had defects. Test the foreman's claim that less than 5% of products have defects with a significance level of 0.01. Okay, so first off, what are we going to be testing? We're going to be testing a claim regarding the population proportion P. So let's go and write that. Population proportion of defected products. Okay, so we're going to be building our null and alternative hypothesis based off of this population proportion of defected products. All right, so let's go ahead and define our null and alternative hypothesis. It should always be your first step. Define your null and alternative hypothesis. Okay, and it's going to be based for P, the population proportion. And the claim is that less than 5% of products will have defects. So that means P, the alternative hypothesis will be that P is less than 0.05, right? Less than 5%. And so then the null will be that P equals 0.05, right? Okay, so this is a left-tailed hypothesis test because of this less than sign in the alternative hypothesis. We're interested in knowing if P is less than 0.05, so that's the left side of a distribution, left tail of the distribution. Okay, next step is to calculate our test statistic. Now, formula for the test statistic is P hat minus P divided by PQ over N. All right, so we're going to need to know what is P hat. So let's go ahead and calculate P hat. Reading this information, they've told us that they've collected a random sample. There are 40 defects and out of 845 products. So 40 divided by 845 is 0.0473. Okay, so now I have all the information I need to calculate my test statistic. So 0.0473. Now what's P? We look to the null hypothesis. Remember, you always look to the null for what is P in your calculation of your test statistic. So 0.05 divided by P, which is 0.05, times Q, which is 1 minus P, so that'd be 0.95, divided by N, which is 845, right? That's the sample size. So there are 845 products that were sampled. Right. If we calculate this, we get negative 0.0027 in the numerator. In the denominator, we get 0.0075. It's a good idea to not round too much in your in the steps to get to your calculation of your test statistic. Remember, your test statistic needs to be calculated accurately up to 2 decimal places. So rounding to 4 decimal places in intermediate steps is probably a good idea. Okay, so go ahead and divide those two numbers and you get negative 0.36. So our test statistic is negative 0.36. All right, so I've defined my null and alternative hypothesis. I've calculated my test statistic. Next, I either do critical values or p-values. Okay, so that's your next step. I'm going to start with talking about getting the p-value. I think that is the more useful way to make a conclusion nowadays, though I will also talk about the critical value and how to use that. All right, so starting with the p-value, so let's consider our distribution of the test statistic given HO is true. All right, here we go. Centered on 0. Okay, here is our test statistic, negative 0.36. It's to the left of 0 because it's negative. Okay, and our alternative hypothesis is that P is smaller than 0.05. So this is a left-tailed test. So the p-value then will be the area to the left of our test statistic, because this is a left tail test. Okay, so the p-value will be to the area to the left of negative 0.36. So I go to my table and I look for 0.36, negative 0.36. So here's 0.6, it's on that row. And 0.3 is down here. So 0.3594. 3594. Right, so our p-value is 0.3594. Right, which means that it's not, that is a large area, 0.3594. Right, and it's larger than alpha. Right, in this problem, alpha, the significance level was 0.01. So alpha is 0.01. So this area is larger than alpha, which means that it's not unreasonable that this value came from this distribution, right? This value, negative 0.36, is not an extreme value, right? It's not a value that is really in the tails of this distribution. So it's reasonable that this negative 0.36 came from the distribution where the null hypothesis is true. So our conclusion is going to be that we're going to fail to reject the null hypothesis. All right, let's say we decided to do this problem using critical values. You'd only do one or the other, but for the sake of practice, let's talk about how would we do the same problem using critical values instead of using a p-value. All right, so we would think about the distribution of our test statistic given HO is true. Okay, you always start with that. All right, and then you determine what side tail is this test. This is a left tail test, right? And so we have a cutoff value for which if our test statistic is in this tail of the cutoff value, then we'll reject the null hypothesis because we'll say, oh, well, it's extreme. It doesn't appear to have come from this distribution where the null is true. All right. So we just need to determine what is that cutoff value. Well, the area back there, the area that is in this tail, so let me go ahead and erase this so I can draw what that area is. So area is alpha. In this case, alpha is 0.01. So this area back here is 0.01. Okay, and so we need to know what is this critical cutoff. I'm going to write Z subscript with a little c for critical cutoff. What's this cutoff for where the extreme values of the test statistic are considered to be? All right, so to do that, I go to my table, and I look inside the table, and I try to look for 0.01. Okay, so 0.01. All right. All right, so 0.01, it's between these two numbers, 0.0102 and 0.0099. It's closer to 0.0099 because it's only 0.0001 away from 0.0099. So it's closer to this number, so we'll go ahead and choose that number. So that's negative 2.33. So the Z critical value will be negative 2.33. Okay, so this critical value is negative 2.33. Right, and then if you observe a test statistic that is in this critical region or this rejection region, so it's beyond negative 2.33, then you reject the null hypothesis. However, our test statistic value is here at negative 0.36. So it's not in the rejection region, so we would not reject the null hypothesis. So you see, whether you use the p-value or use the critical value, you'll get the same conclusion, okay? It's just different ways of getting to that conclusion. So let's go ahead and get to our final step, which is to state our conclusion. So we've decided that we're not going to reject the null hypothesis. So we write that as fail to reject HO. Right? So remember, the null hypothesis is that P equals 0.05, and the alternative is that P is less than 0.05. Okay, so we failed to reject this possibility that P actually does equal 0.05, so that means there's not enough evidence to support the alternative. Okay, so there's always two parts to your conclusion, one part about the null, second part about the alternative. So there is not enough evidence to suggest that the proportion of defects is less than 5%.